Hello, and welcome to the third module out of five regarding piston and cylinder example problems. We're getting a little more complex, so let's see where we're headed. So what we'll do is we're going to do two example problems. First one, of course, be in SI, and the second in English. They'll be very similar, but so important to be able to master both sets of units. All right, first problem. I've got to move my Zoom menu here. Just going to have to pardon me a second. There we go. A gas is contained in a vertical cylinder fitted with a piston on the top and closed on the bottom. Sounds familiar, doesn't it? The initial volume of the gas is 0.25 cubic meters, and the initial pressure is 900 kPa. The gas undergoes a quasi-equilibrium process with a path defined by P times V, pressure times volume, equals constant, and the volume triples during the process. Determine the final pressure of the gas and determine the work done by the gas during the process. Two simple questions, maybe not quite so simple to find. So let's go through and look at the mechanics of how to solve this piston and cylinder problem. Okay, we'll look at the key words. Vertical cylinder fitted with a piston. My suggestion is when you start with your sketch, write down the word closed system somewhere on your sketch. That's worth something. At least that that you're demonstrating that at least you understand that a piston and cylinder is a closed system instead of an open system. And as we go through this course, we're going to be dealing with closed systems and open systems, and it's not going to be very clear which is which. So you'll be able to demonstrate that you've got that mastered. All right. The initial P1 and V1 are given in this problem. So that's a key. Okay. Key quasi-equilibrium process, it's just clearly stated, come out in the process. It's clearly stated, not even, doesn't talk about frictionless, it just states quasi-equilibrium. Now, the PV process is defined where it says PV equals constant. That's a key to pick out, where it says the pressure multiplied by the volume, those two properties, equals a constant number. All right. Also, what's given is that the volume triples, so you might as well write down V2 is equal to 3V1. That's easy. And then you will discover, as you study this, you'll discover that since P1 and V1 are both given, you're going to be able to use that process path statement to determine P2. And then determine the work done. Since it's quasi-equilibrium and a closed system, you're going to see that you will start with the fundamental work out equals the integral of PdV to determine the work. All right, so let's start with our sketches. For this problem, you need two sketches. You do not need the free body diagram for this problem because there's enough information given in the problem that at least you know the initial pressure. And so you're not going to have to mess with a free body diagram for this problem. So do you see that when you go through this whole class, it's not like this rote recipe of here's what you have to do, bup, 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 bup. You have to use your head after you've read each problem. So we've got two sketches needed for this problem. The equipment sketch, here it is. See, I'm just depicting my closed system with my dashed line, control surface, showing heat in, work out, and showing a second state where let's see, the volume is tripled and then the pressure is doubled. Okay, so anyway, so there's our equipment sketch. It's very worthy to draw that out by hand. It is absolutely necessary to draw the pressure volume diagram for this problem in order to, to visualize the work done. As you can see, area under the curve. And you also have to be pretty good at diagnosing what is the mathematics of PV equals constant. You got to get good at this now. Okay. PV equals constant is another, so let's reword that. P is equal to constant over V. Just divide both sides by V. And then remember that P is kind of like Y, and V is kind of like X. It's exactly like that, all right? And so you go back to high school, and what does Y equal constant over X looks like? Or Y equals A over X, or even Y equals, let's just say 1 over X. Y equals 1 over X. Y equals A over X. What is that? Think in your mind. Can you answer that with me saying the result? I'm going to say it in a second, but think in your mind. Y equals A over X. What's the name of that curve? It's a hyperbola. You should know that. So we expect you to know that from high school. And then at a minimum, freshman calculus. So that PV equals constant is a hyperbolic process path. And so I have drawn this in as a hyperbola. Okay. And so P is equal to constant over V. And then since with the given information, you're given P1 and V1, so that's the constant. So you might as well write out constant P1 V1 divided by V. That's the shape of this hyperbola. All right. So that's the setup. You're going to get good partial credit if you get this far. So the work is the integral of P dV. You see, it's going to be a positive number because you're integrating left to right, state 1 to state 2. I've shown the hyperbolic process path along with an arrow. Okay. And now we can plan for the integral. Let's plan for the integral. You've got it. Okay. Area under the curve. I got that part. All right. P1, V1. I've got both of those. All right. So let's just, without crunching numbers, let's write out your formula. Okay. You've got to be able to perform this integral, by the way. That's my little note here. Work out equals the integral from V1 to V2 of P dV. Next step, write in what is the process path for pressure. The process path for pressure in these brackets is constant over V. Okay. Well, the constant is P1 V1. And so what I'll do is I will pull P1 V1. That's a constant, it's not a variable. So I'll pull that out of the integral sign. And so you must be able to perform this integral right here. So I'm going to work you through it, but think in your mind before we go to the next slide. Do I know how to do this? Do I know how to do this integral right here? Okay. So some more friendly advice. You might, if you can't do the integral, you might start searching in your textbook, because I'm going to look for an example problem, or I'm going to look for some reading in the text where I'm going to get the formula for this, the special type of process where PV equals constant. I may be able to fish out a formula from the book for this. I want to suggest that's not a good approach. For success in quizzes and tests, you must be able to figure this out on your own rather than seeking a formula. Okay, so let's do it. Let's do the math. Workout is equal integral P dV equals P1 V1, pull it out of the integral of 1 over V dV, also known as dV divided by V, but in 1 over V dV. Let's see, that's also V to the minus 1 dV, right? So there's something special about this formula that you can't increase the exponent by 1 and do that traditional, like you're integrating V squared dV, right? That would be a totally different integral, V squared dV. This is V to the minus 1 dV. And so you recognize this as a special case. It's natural log. 1 over V dV is the natural log of V evaluated from 1 to 2. And so I've got a typo in here and I've missed that. So it's the natural log of V2 minus the natural log of V1. And I see that this is a typo, so I've got to apologize here. This is the natural log of V2 minus the natural log of V1. I need to make a note on slide 8 to fix this. So just excuse me a second. Slide 8, I've got to fix. Okay. But I've done it. I've corrected my careless error. And the next step is the log of V2 minus the log of V1 is the log of V2 over V1. Okay, so you got the workout. Now it's easy. P1, you know it. V1, you know it. The log of V2 over V1. What's given? The volume triples. So it's the natural log of 3, which is a couple of presses on your calculator. All right. And so there we go. Numerical evaluation for P2. So now we're going to do the numerics of the problem. How are we going to get P2? Well, PV is constant. And so it's just a matter of saying, look, P2 is 1/3 P2 equals P1 V1 over V2. And so P2 is 1/3 of P1. Volume triples, right? So V1 over V2 is 1/3. All right. And so I went in and I did the numbers here. Here's P1, here's V1. Just because I do my work in Excel, I calculated the constant P1 V1, okay, to get V2. V2 is 3V1, 0.75, and so P2 is 300 kPa, 1/3 of P1. Now, it looks like I did catch my careless typing over here in this one, determine the work done here in this slide. So I repeated, and I did catch this here just a couple of minutes ago to see, do the math. Let's do the units check for the work out. And so let's look at this final result. How about what are the units of the natural log of V2 over V1? Do you see that that is unitless? So all I have to do is look at the units of P1, V1. So P is in kPa, kilonewtons per square meter. V1 is in cubic meters. And so my resulting units are going to be kilojoules, kilonewton meters or kilojoules. And so really it's pretty easy math once you go through the mathematics, pretty easy calculator work once you go through the math. And so the workout is 247.19 kilojoules. Okay, not bad. But you do need to be able to do that integral. All right, example 2, we're going to go through, it's going to be very similar. I just changed the numbers to be very careful that we can also go through and get the correct English units version of the same problem. All right, 3.1 cubic feet is the initial volume, initial pressure 200 psia. The same process path, PV equals constant. The volume still triples. Let's go do the work again. Boy, let's see if I made that same blunder over on this side. Numerical evaluation for P2, well, that's exactly the same approach, right? P2 is 1/3 of P1, okay? And so P2, now you see in my solution, I kind of drug this solution out. There's no need to do that. Notice here how I converted P1 into pounds force per square foot. In order to calculate my constant value, P1, V1, that's not necessary to do that. You could just go calculate P2 direct from here with P1 given and express your P2 in 66.7 pounds per square inch. That works too. The only reason I do this is for my own habit, my own problem-solving habit. I tend to do better when I can do the same things over and over again, and I keep myself straight that way. And I've done that throughout my student life and career as well. So anyway, that's just the way I've approached the solution. You may choose to approach it differently and stay in PSI. That works. Oops. All right, now the numerical evaluation of the integral. The English units check is very important. Let's check the units of P1 V1 natural log V2 over V1. Remember, the natural log of any number, it's got to be unitless. So there's no units associated, unity are the units associated with this term, natural log V2 over V1. P1 V1, pounds per square foot. Definitely use pounds per square foot for your pressure and cubic feet for your volume to get foot-pounds force, okay, such that you'll express the work out in terms of foot-pounds force. Okay, there it is, 98,084 foot-pounds force for this set of input data. See how that's so important in English system to check those units. Otherwise, you'll blindly get some crazy number and you'll get a big X next to it because the units will not have worked out right. And you'll be frustrated because you say, but I did everything else fine. Look, if you don't show your work, imagine the terrible situation where if you do not show your work and you overlook your units check and you write down some number, boy, you are going to get murdered in a quiz or test, right? Now, showing your work and not checking your units is not nearly as bad as not checking your work and not checking your units. Okay, so what did we learn from this module? Start with a sketch, look for the keywords, keep your units straight. Seeking formulas in the textbook might work. And you say, well, okay, and I'm going to get this, I'm going to put that on my formula sheet. I got that formula and I used it on a homework problem. I'm just going to write it down on my formula sheet. And the pitfall on that is you don't know what that formula applies to unless you're very careful in creating your formula sheet. So looking for formulas and writing formulas down from the textbook is poor prep for quiz or tests. And so my recommendation is derive your own formulas from the fundamentals. I hope that helps. Wow. So I hope that helps you. And so we got a little more complex on the math for this problem. Next module, we're going to get even more complex on the mathematics. Hope this helps and hope you tune in for the next module.